Second half of chapter 2, and this is why I split it. The first half is really learning about limits, how do you evaluate limits, everything like that. Now we're going to see how limits can be used to define what a derivative is. So getting into finding derivatives. Chapter 3 then is all on methods to find derivatives. Chapter 4 is on applying derivatives, so we're going to be working with derivatives through Chapter 4, well, through the end of the year, but really through Chapter 4. Chapter 5 is when we start integrals. So we revisit tangents and then velocities as well. We're talking about tangents first because those two problems were used to help give you the idea of what a limit was. So we talked about how finding the slope of a tangent line, it was the limit of slopes of secant lines. And we're going to revisit that idea again. But now because we have learned about limits and we've learned ways to evaluate limits, we can now find slopes of tangent lines in an easier way or a more practical way, I guess I would say. There's a certain limit or certain limits you can use to find slopes of tangent lines versus just having to pick certain values and estimate what the slope would be. So at the top, this is kind of revisiting the idea we already talked about, but it's coming up with why we use the limit we use to find the slope of a tangent line. It says if a curve C has an equation, so this is just in general, y equals f of x, some function, we want to find the tangent to C at the point P, and these are the coordinates of point P, so the x coordinate is A, and the y coordinate would be whatever f of A is. Then we consider a nearby point Q, and Q would be any other point that's also on the curve, so with any x coordinate, and then f of x would be the y coordinate, where x doesn't equal A, and we compute the slope of the secant line PQ. So if we look at this diagram here, this is showing here's your point P, shows the coordinates. We're choosing this nearby point Q, and then they only have that segment drawn in, but if that was extended, what we're doing is we're calculating the slope of that secant line. So if we use our slope formula, I'll just put a slope of PQ here. I can use slope formula to come up with a formula for the slope of any secant line, and that would be the change in the y value, so it'd be f of x minus f of A, over the change in the x values, x minus A. So no matter what point Q you're choosing, we can use that formula. We're just calculating the slope between the points P and Q. And then what it says underneath here, so then we let Q, and these are the ideas we've already talked about in 2.1. We let Q approach P, so we chose points Q that got closer and closer to P along the curve C by letting the x values approach A. And then if the slope of PQ, so that secant slope approaches a number m, then we define the tangent T to be the line through point P with slope m. So it says this amounts to saying the tangent line is the limiting position of the secant line PQ as Q approaches P. And that was how we kind of started talking about limits in the first place. So this here is then showing if we started with this Q and we're letting Q get closer and closer to the point P along that curve, ultimately this is our tangent line that we're finding, but those secant lines are approaching that tangent line as Q gets closer to P. So because the slope of a tangent line is then considered a limit as your x values from point Q approach the x value of P, which is A, and these are all the slopes of your secant lines, we then have this definition of a limit we can use to find the slope of any tangent line to any curve. So the tangent line to a curve y equals f of x at the point P with coordinates a f of A is the line through point P with this slope, and to find the slope you calculate the limit as x approaches A of your secant slopes, f of x minus f of A over x minus A, provided that the limit would exist. If the limit doesn't exist, that means there isn't a tangent line because if the slope of the tangent line is that limit. If it doesn't exist, we don't have a tangent line. So then in example 1, this is actually the problem we looked at in 2.1, that first example, where we had to find different points Q and find the different slopes. We're going to revisit this example, so find the equation of the tangent line to the parabola y equals x squared at the point P with coordinates 1, 1. All right, here's what you have to do. To find the equation of any line, so we're finding the equation of a tangent line. So thinking back to algebra, if you need to find the equation of a line, you need a point and you need a slope. We have a point, we do not have a slope, so we need to find the slope of the tangent line. And to do that, we use this limit. And in this limit, what you need to know is you need to know what f of x is, and you need to know what your a and your f of a are. So we are given our point P, and again, these coordinates, the x coordinate is your a value, and then the y coordinate of point P is f of a. And your f of x is just your curve. So if we have y is equal to x squared, that's our f of x. It's just your function that you're using. So in this case, it's x squared. So if I were to set up the limit to find the slope of this tangent line, and I'm going to use this information I have using this formula, I'll have the limit as x approaches a, means x is approaching 1, of my f of x, my function is x squared, so I'm going to replace the f of x with x squared, minus f of a, the y value for p is also 1, so x squared minus 1 over x minus a, so x will always just stay x, and then minus a is 1. So this is the limit I need to evaluate in order to find the slope of the tangent line to this curve at that point. Are there questions just on setting this up before we move on to actually evaluating it? Okay. Now, evaluating the limit, you've done this. This is what we just spent the previous 5 sections of Chapter 2 doing. Always use direct substitution first. So if I substitute in 1, I'm going to get 0 over 0. And that's indeterminate. So what do I need to do so that I can evaluate this limit? Factor the top, yes. And make sure I have not, if I'm now rewriting the function, I haven't actually taken the limit yet. I should rewrite the limit as x approaches 1. Factor x squared minus 1. So that's a difference of squares, x plus 1 times x minus 1. And then I still have x minus 1 in the denominator. And then, yes, the x minus 1s cancel out. So you just have the limit as x approaches 1 of x plus 1, and now I can use direct substitution again to get 1 plus 1, which is 2. So the slope of my tangent line is 2. What? Right, that's just the slope. No, we're not done. So if you don't have to do this right now, and I'm not going to force you to do it anyway, but if you looked back at 2.1a, the first example, we had this whole process just to get the number 2. This has shortened that process because we now know how to evaluate limits. So that's why we're revisiting this, the tangent problem. So we have our slope. So now to write the equation, if my slope is 2 and my line goes through P, which has the coordinates 1, 1, now you're using algebra to write the equation of this line. So I typically will substitute my slope and point into the point-slope form. But if you like to substitute it into slope-intercept form, solve for B, and then rewrite the line, that's fine too, however you get there. So if I substitute in what I have, I'll have y minus my y coordinate is 1 equals the slope is 2 times the quantity x minus, and the x coordinate is 1. It is perfectly acceptable to leave this equation as your answer. You can leave it in point slope form. You don't have to, but what I want you to realize if, I'm always kind of thinking ahead to the AP test. So if there was a multiple choice question, if they had all of their choices in slope-intercept form, then you would have to solve for y to see what the equation was. If it's a free response question, you can leave your answer like this. And I would probably recommend doing that because say you tried to solve for y and you made one little mistake. Now you went from an answer that was right to an answer that's wrong and you won't get the points. So if you would have left it, you'd get the points. If you rewrite it wrong, you don't get the points. So yes, you do, there's kind of a balance. You have to know how you would simplify, but when it comes to free response, you don't necessarily have to, especially since the simplifying is algebra. The simplifying isn't calculus. So you can leave it this way. Sometimes you'll see equations written like this where they'll just add, they'll keep this as 2 times the quantity x minus 1 and they'll just add this 1 over. So you might see equations written this way, y equals positive 1 plus 2 times the quantity x minus 1. Sometimes they'll write it like that. Or they might just go and fully simplify it into slope-intercept form. So distribute the 2. So this would be another way that you could write it technically. Or you could have y equals 1 plus 2x minus 2. So y equals 2x minus 1. Slope-intercept form would be another way you could write it. So multiple forms for your answers. But again, you don't want to make a simple algebra error and then lose points when it comes to a free response question either. Okay? No. Nope. Unless, I mean, they usually don't specify what form they want it in, but if they did, then it would matter. They typically don't. Carissa? Well, yeah. I mean, if you can use slope-intercept form. That's fine. Yeah, they typically don't say write the equation in a specific form. They just want the equation. So I was just showing here, if you start with this, you can leave your answer this way. Yeah, and that's fine. All right. Are there questions on that example? So you're using a limit to find the slope of a tangent line. You have to know this limit. You have to know that formula of a limit. You have to know that. You should ideally use it enough that you just remember it anyway, but you do have to know it. All right, there is another expression that is not the only expression you can use to find the slope of a tangent line. And there's another expression that is sometimes easier to use. So this expression, when we get to it, will probably look familiar to you. It involves h. So if we let h be equal to the expression x minus a, then if I solved this equation here for x, so I added a to each side, x would equal a plus h. So therefore, what I'm doing is I'm rewriting the formula we already have to get this new formula that involves h. So then the slope of a secant line PQ, which we wrote before as f of x minus f of a over x minus a, if I now rewrite the x's with the expression a plus h, I will get the formula f of x is now a plus h minus f of a stays f of a all over, and then in place of x again I would have a plus h, but then I have minus a. So in the denominator, the a's are going to cancel out. So I just have f of a plus h minus f of a all over h. Well, so this is just an alternative, yes. So now if x is approaching a, then if you look at how h is defined, if x approaches the number a, the difference between x and a gets smaller and smaller and smaller. That difference approaches 0. So h is going to approach 0. So to go from, this is just the slope of a secant line, the slope of a tangent line is a limit. So now as the slope of the tangent line, we have the limit as, and since I don't have an x, I no longer want to say as x approaches a, because x doesn't appear in this expression, as h approaches 0, of f of a plus h minus f of a all over h. This is just an alternative limit you can use to find the slope of a tangent line. And sometimes it's easier. It is really your preference, but sometimes the one with h is easier. So what I'd like to do is go through the example we just did. We don't have to write the equation again, that part's the same. But use this limit to find your slope just so you can see the difference between the two limits. We'll still get the same slope of 2 as long as our math is correct. So this is the same problem. Find the equation of a tangent line to that parabola at 1, 1.
I checked the last 3 and to make sure that it was all equal to 2, so I should be fine.
Yep, see you later. All right, so if we go ahead and find the slope using this new limit, all we have to substitute into this formula, we know a and we know f of a. So our a is still 1. F of a is still 1. So we would have the limit as h approaches 0 of f of, our a value is 1, so f of 1 plus h minus f of 1, f of a we know is 1, I'm just going to put 1 there right away, and then all over h. Right, well if you substitute, it's not undefined because you get 0 over 0 again. But we can still rewrite this. The f of 1 plus h, this means if our y equals x squared, this is our f of x. This means I'm replacing the x in my function with the quantity 1 plus h. That's what f of 1 plus h is. So I would have the limit as h approaches 0 of, and f of 1 plus h instead of x squared would be the quantity 1 plus h squared minus 1 all over h. Now you still can't use direct substitution. You're still going to get 0 over 0. But how would I rewrite this to evaluate it? Yes, expanded, or I heard FOIL because it's 1 plus h quantity squared. I'm glad I heard FOIL and not distributing the exponent. Don't do that. Well, it might be fun, but it's not going to get you a right answer. So this is 1 plus h times itself. So that would be 1 plus 2h plus h squared. And then I still have the minus 1 all over h. So you've evaluated limits like this. I've given you problems already that are set up this way. And I think I've even referenced that we'll use them a lot later. what will always happen as long as your algebra is correct, and I prefer this form for this reason, is once you simplify your numerator, you should always see that any term without an h should cancel out. So here the positive 1 minus 1 cancels, and that means everything that's left has an h that you can factor out, so your h cancels in the denominator. So if I factor out an h right away on the top, I still have the limit as h approaches 0, but I would have h times the quantity 2 plus h all over h. And now my h's cancel, so that I'm able to substitute in 0 for h, meaning my limit is 2 plus 0, which is 2. Okay, and that's still the slope. You would then go ahead and write the equation, but again, we wrote the equation in part 1. The equation part is still the same. This is just an alternate way to find the slope. Okay, any questions on that limit? What I would recommend, because ultimately if I just ask you to find the slope of a tangent line or find the equation of a tangent line, it doesn't matter to me how you find your slope. It doesn't matter to me which limit you use, this one or the first one. But if you try one and you're not getting it to work out algebraically, try the other one. So the reason I prefer this one, not that it's the best one to use every time, is because all I have to try to do is cancel out an h in the denominator, versus in the other formula, you're trying to cancel out an x minus a. So there's just less to cancel. There's one term to cancel versus an expression, or two terms. So if we look at example 2, this one I'd like to go through together just because of how the limit is going to turn out. So it says, find the equation of the tangent line to the hyperbola y equals 3 over x at the point 3, 1. So I guess I'll ask you preference on which limit to use, the first one or the second one. I heard the second one first. Ultimately, it doesn't. If you wanted to try with the first one, you should get the same slope. So I'm just going to rewrite the limit. So we have, if you would like to use the first one, do it and see if you get the same answer. Okay. So this means, what's our a value in this problem? A is 3. So I have the limit as h approaches 0 of f of 3 plus h minus, I'm just going to put f of 3 here for now. I know I can fill that in, but then over h. Rewrite limit as h approaches 0. So f of 3 plus h means in my function, which is 3 over x, I'm replacing the x with 3 plus h. So that becomes 3 over 3 plus h, and then minus f of 3, our f of a is just 1, and that's all over h. So I have a complex fraction.
Oh, okay.
3 over 3 plus h. So f of 3 plus h is your function, which y is f of x. So it's your function evaluated at 3 plus h. So you're replacing the x in your function with 3 plus h.
Why did you just go right away?
You could have. I could have put 1 here right away. Yep. Yeah, if you put 1 right away, that's fine. No. Any questions just on the setup part? Okay. So then the question is, you can always check, but I will tell you what will always happen is when you substitute in 0 for h, you're going to get 0 over 0. And that does happen here. We'd have 3 over 3, which is 1, minus 1 is 0, over 0 in the denominator. So we have to rewrite this so we're able to evaluate it. How can we rewrite this expression? Wait, say that again. What did you say? 1 plus. Like just the 3's over 8? Oh, I see what you're doing. You cannot split a denominator. You can if it was the reciprocal, if it was 3 plus h over 3, then you could split a numerator into 2 fractions. We can't split a denominator. I was just trying to picture what you were saying. Okay. I'm done. We could do that. We could write this 1 whole. It would kind of be the equivalent if this is 1 over 1 as multiplying it by 3 plus h over 3 plus h, so that you have a common denominator on the top. So this, I will say, evaluating these limits, this is all algebra. This is all review of algebra. So reviewing a lot of algebra in limit problem. So I would have 3 over 3 plus h minus 3 plus h over 3 plus h all over h, which then, you just have to be careful with this. I can write the top then as 1 fraction, but you have to make sure the quantity in the numerator is being subtracted. So you would have to distribute that negative through. So I would have 3 minus h all over 3 plus h, and then that's all over the h in the denominator. So the 3 minus h is the 3 minus this quantity, combining this numerator into 1 fraction. And then these 3's are gone. So I really have, I'm just going to rewrite this here. I have negative h over 3 plus h all over h. The h will cancel. Yes, so a way to think of this, if you can't see looking at this that it cancels, this h in the denominator I could write, there's a few different ways I could show this, but this h in the denominator, if I'm dividing this whole thing by h, it really means I'm multiplying by the reciprocal of h, so I'm multiplying this top fraction by 1 over h. That's what the dividing by h means. So then these h's cancel each other out. So I do have the limit as h approaches 0 of negative 1 over 3 plus h, which now I can substitute 0 in for h to get negative 1/3. So, and this is what I'm saying is, if you try one, even if you tried this way and you're not getting it to work out algebraically, try the other one. You have 2. In some cases, 1 might be easier. It's not always that the one with h is easier. I just find there's less that you have to worry about canceling out that makes the denominator 0, but it doesn't mean it's easier in every case. Okay? As x approaches 3. I will look at yours while you're getting -1/6. So to finish this problem, though, make sure, because this is a lot of work, you're not done with this question. Don't leave this here. You have to find the equation of the tangent line at this point. So if m is -1/3, your point is 3, 1. You have y minus 1 equals -1/3 times the quantity x minus 3. Whoops, you can't quite see that whole thing. Here it is. It is fine to leave your equation in that form, but you can write it in slope-intercept form if you'd like.